Hello, good morning everyone. This session is for BSc course paper 8 biochemistry session number 26, which is a continuation of biological oxidation. In the previous session, I have told you the criteria for delta G for spontaneity of a reaction, and in this session I am going to tell you about ATP as a currency of the cell and some of the examples for high energy phosphates. So these are the contents: high energy phosphates, definition and example, and ATP as an energy rich molecule and examples for high energy phosphates other than ATP. So what are these high energy phosphates? So the phosphate esters and phosphoanhydrides upon hydrolysis gives a large amount of energy, and they are called as high energy phosphates. And why do they give large amount of energy? See, these high energy phosphate bonds are usually pyrophosphate bonds, acid anhydride linkages, and how are they formed is, if you take phosphoric acid derivatives and dehydrate them, means removal of water molecule, will yield these pyrophosphate bonds. Okay, and when they undergo hydrolysis, they releases large amount of energy. Okay, and therefore these reactions are exergonic reactions under physiological conditions and they release large amount of energy. Examples are nucleotide pyrophosphate such as ATP, enol phosphate such as PEP or phosphoenol pyruvate. See, all of you know very well that ATP is called as the currency of the cell. See, this ATP-ADP cycle is continuous. You know very well in catabolism, that is through photosynthesis and cellular respiration in all organisms. These are all called energy yielding reactions. When they break down through cellular respiration, broken down into simpler molecules, a complex molecule is broken down into simpler molecules with the release of ATP. Look here, with the release of ATP. And this ATP is used in the biosynthesis of macromolecules. Okay, in the biosynthesis of macromolecules. And these require energy. That is, they utilize this energy. ATP upon hydrolysis gives a large amount of energy and ATP itself converting into ADP and PI. See, this is a very important cycle that is taking place. That is ATP ADP cycle. Okay. So through catabolism, ATP is released. The anabolic reactions utilizes this ATP, again giving back ADP and then PI. Okay. Now a very interesting question is why ATP is an energy rich molecule. Okay. And it's an energy reservoir in the body. Okay. So it is a universal energy currency, just like when you for your mobile, when you recharge the currency, your mobile gets charged. Similarly, for a cell, ATP is known as the currency of the cell. See, in almost all the reactions, in biochemical reactions, they are associated with this hydrolysis of ATP. So when ATP undergoes hydrolysis, it produces ADP and inorganic phosphate with a release of minus 30.5 kilojoules per mole or minus 7.3 kilocalories per mole. So this is a spontaneous reaction, exergonic, and therefore it's a thermodynamically favorable reaction. Now, what are the factors that makes ATP as an energy-rich molecule is electrostatic repulsion within a molecule, solvation, and then resonance. We'll take one by one. So it's a very important question for you even from the examination point of view, which you will get for 4 marks. Write the structure of ATP and what are the general characteristics or the general features that makes ATP as a high energy compound. See, this is the structure of ATP. Okay, adenosine, triphosphate, adenosine triphosphate. When it undergoes hydrolysis, what you get is ADP. See, there are 3 phosphate groups here. There are 2 phosphate groups here. This is adenosine diphosphate plus inorganic phosphate. And this is a spontaneous reaction, exergonic reaction, a thermodynamically favorable reaction. So you look at this, the structure of ATP. Structure of ATP. See, you are seeing a large number of negative charges here. Are you observing? O minus, O minus, O minus, O minus. There are 4 negative charges. So obviously, there is an electrostatic repulsion in the molecule. There is an electrostatic repulsion in the molecule. So, it has got 4 negative charges while ADP has 3 negative charges obviously. See, more the number of negative charges, more is the electrostatic repulsion within the molecule and lesser is the stability. Hence, ATP is less than the product of hydrolysis of itself. Therefore, ATP serves as a high energy compound. It easily undergoes hydrolysis because the product's forms are more stable than the reactant. The second reason why which makes it as a high energy compound is hydration or solvation. See, hydration is the ability of a molecule to be surrounded by water molecules. Hydration is directly proportional to the stability and inversely proportional to the size of the molecule. See, ATP with a bigger size undergoes less hydration and hence possesses less stability. Okay, whereas ADP when compared to ATP, smaller size, undergoes more hydration and hence possesses high stability. Okay, now coming to resonance. So the negative charge on the oxygen atom in ATP is delocalized, resulting in 2 resonating structures that exist in equilibrium. Okay, whereas in ADP, the negative charge on oxygen atom in ADP is delocalized, resulting in 2 resonating structures that exist in equilibrium. Okay. So, on a whole, products have 6 resonating structures while reactant have 2 resonating structures. Okay, the products are more resonance stabilized than the reactant. The products are more resonance stabilized. See, 4 here, 2 here, so 6. So, the products have more resonating structure when compared to the reactant. So, you know very well now why ATP is more energetic and high energy compound when compared to ADP are the structural features that makes ATP as a high energy compound is because of 3 reasons. One is electrostatic repulsion, second one is hydration, next one is the resonance. Okay, the product of hydrolysis are more stable than the reactant itself, therefore it easily undergoes hydrolysis, and the hydrolysis of ATP is an exergonic reaction and thermodynamically favorable reaction. Now, so there are some other high energy compounds, high energy phosphates, which will give more delta G naught that is the free energy when undergo hydrolysis. Therefore, they are known as super high energy compounds. And which are some of the examples of super high energy compounds are pyrophosphates, that's a more than ATPR. Enol phosphates is phosphoenol pyruvate and acyl phosphate is 1,3 biphosphoglycerate. Okay, usually they'll ask you the structure of this. Name and write the structure of any other compounds which are highly super high energy compounds other than ATP. So you have to write phosphoenol pyruvate and 1,3 biphospho or diphosphoglycerate. If you take thiophosphate, it is acetyl CoA. Okay, so you should know to write the structure of these two, phosphoenol pyruvate and 1,3 biphosphoglycerate. So look here, why I told them as a super high energy compound is, see, this is the energy that is released in kilojoules per mole when they undergo hydrolysis. So they are known as high energy compounds. That is phosphogonadines, enol phosphates, phosphoric carboxylic compounds, phosphoric acid anhydrides, and thioesters. So these play a very important role in biochemical reactions because the hydrolysis of such compounds will give lot of energy, which are spontaneous and exergonic reactions. Okay, so in this session we have learned the currency of the cell is ATP, and what are these high energy compounds, and the structure of ATP, and the structural features that makes ATP as a high energy compound, and examples of high energy compound other than that of ATP. Thank you.